Welcome to this lecture series in number theory. Last time we discussed the notion of inverses. We defined what is meant by an inverse of a given integer modulo a natural number n. But in today's lecture, we will discuss something that is unrelated to inverses. We ultimately want to characterize when exactly do inverses exist and what not, and that is one of the main goals of this particular module. But we will kind of switch gears for the moment just to introduce a different viewpoint on modular arithmetic, which will be very useful for us in terms of exposition as well as comfort in thinking. It will facilitate us to think in ways which make our lives easier and reduce or eliminate all possible confusion. The price that we have to pay for it is that we have to get acquainted to a new point of view and sort of a new language. However, I hope you find all of this very interesting. By all of this, I mean all of what is to follow. And what do we need to know? We need to be familiar with the language of functions, relations, sets. Well, this I already assumed even before we begun this course. And if you want to really brush up, you can refer to my playlist named Kickstart, or you can do a quick Google search, go to Wikipedia, read from whatever text you like. All right, we of course need to know about congruences and modular arithmetic, namely these two facts about modular arithmetic. Okay. More recall, we discussed the congruence relation modulo n. So fix a natural number n. We discussed the congruence relation modulo n as, and what did we define it to be? It was a relation on the set of integers, which was defined as for x and y in integers, we write x congruent to y x congruent to y if x minus y is divisible by n. Well, by now we are comfortable with modular arithmetic, so I shouldn't have recalled this. And yeah, instead of writing x and make the symbol y, we also write a mod n because this relation is sensitive to n. Okay, so this was what we referred to as the congruence relation. I was just trying to recall the name of this symbol. This is referred to as the congruence relation modulo n. In this notation, n is missing. We are suppressing n, but you may like to put a subscript here if you want. Okay. These were some examples of congruence classes. So the equivalence classes under the congruence relation are called congruence classes. And this was an example that we had given. These are all the congruence classes mod 4. So the pink one, all the pink things together form one congruence class or one equivalence class modulo the congruence relation. The green ones form another equivalence class, and so on and so on. And there are a total of 4 equivalence classes. They can be denoted like this. So I don't know if I had made a point somewhere, but the equivalence class modulo n, I don't know if I want to write it separately, but the equivalence class of x modulo, under the congruence relation modulo n is denoted by, or can be denoted by this. I don't know if this is standard. We may drop this subscript if we know from context what is the n that we are talking about. Okay, so the congruence relation was an equivalence relation. Every equivalence relation gives rise to equivalence classes. And the notation for the equivalence class of an element x is this. And here we have an example of congruence classes modulo 4. Okay, all of this we had seen earlier. And here is a simple note. This statement and that statement are precisely the same. So A and B share their equivalence class if and only if they are congruent modulo n, meaning their difference is divisible by n. This is a trivial statement, right? So maybe I will append a little bit to the statement. This is nothing but that said, we know exactly what equivalence classes are, right? The equivalence class of X under the congruency relation modulo n is precisely this set. All things, all integers that can be obtained by adding a multiple of n to X. Take this as an exercise if it is not clear immediately. It should be by now. And the consequence of that statement is this equivalence. So modular, or whatever we say using the modular symbol, if you will, can be expressed equivalently in terms of equivalence classes. It's just that the congruence symbol gets replaced by an equality at the cost of putting ugly brackets. Okay, more recall. We had this notation. What was this notation? This was just a shorthand for all scales of, or the scales of each integer, the scale of each integer by n, or the set of all the multiples of n. That's what nz is. What is a plus nz? So again, a is an integer and n is an integer, rather a natural number in fact, although no harm in considering an arbitrary integer here. But just for simplicity, think of it as a natural number. So a plus nz is what? A plus nz is, just translate every multiple of n by a. Right? And what was z mod nz? So recall this is pronounced as z mod nz. That's the pronunciation. And what was the definition of it? It was this set, which is nothing but the following set. Take this as an exercise. Y is it equal to nz 1 plus nz up to n minus 1 plus nz. Take that as an exercise. Okay, and let me just say that this is another exercise, that a plus nz is nothing but the equivalence class of a with respect to the congruence relation modulo n. A lot of notation, but all of this, this is a pure mess of notation in some sense. But these notations are so interconnected that it may serve to confuse you. But everything is also very easy. And if you just fight with it a little bit, all of this will sink in no time. We have just so many different notations for just one thing, right? Either we can write that, or we can write that, or we can write that, right? All right. So all of these things we have already seen, but I'm just recalling. And here is an exercise to further orient you. Just a very simple exercise. And now with that we can proceed. So now we would like to define a new addition. We have been adding things since high school, in fact primary school, even earlier as children. But what were we adding? We were adding either integers. When we grew up, we started adding rational numbers. We further grew up, we started adding even irrational numbers, real numbers, even complex numbers in secondary high school. But now we will define an addition which will be of fundamentally different nature. But it is a very important shift in the way we think. Nothing very deep is going to happen, but this kind of thinking has gone a long way to help us discover new mathematics and organize old mathematics. This is the modern perspective on how we do mathematics. So, long story short, or maybe without further delay, let me introduce this notion. So before we get to the nitty-gritties, let's look at what is the ordinary addition in a very, very formal light. The ordinary addition on integers. Let's look at that in a very formal light. What does the ordinary addition do? You feed two numbers to it, and it will spit out another integer. So you can think of it as a function. In fact, it is a function. Is a function which consumes two inputs and produces an output. It consumes a pair of inputs from the set of integers and produces an output in the set of integers. So for example, what is the image of 7, 9? Under the ordinary addition, this just goes to the sum of 7 and 9, which is 16. And we may denote this by the same symbol we used to add. So here we would write plus of 7, 9. So plus is your function which consumes a pair of integers and outputs an integer, which is what we call the sum of, what we usually call, or what we call the sum of the entries of the input. And this is what we have been writing as 7 plus 9. That's all. That's when we write 7 plus 9, we are really writing that, but this is not very pretty to look at. It's difficult to work with for us humans. So it's better to write it this way. But really in the background, this is what is going on. And it has several properties, that plus of a comma b is equal to plus of b comma a, which is same as saying whether you add a to b or b to a, it's the same thing, and so on. So everything you know about addition, you can write using this new change of notation, essentially. Okay. So what we are going to do, we are going to define a similar function, not on z, but on z mod nz. And it will have a lot of shared behavior with the ordinary addition. The ordinary addition enjoys a lot of nice properties, like for instance commutativity. You can switch the places of the input, doesn't matter, the output will not change. Associativity, associativity is usually expressed this way. This thing, meaning first you compute the thing in the bracket, and then you compute the result, or you can change the order of addition. Either you add 7 and 9 first and then add it to 8, or you add 9 and 8 first or add it to 7. That's associativity. In the function notation, it becomes much more ugly. So in the function notation, it just says that this is equal to, looks very ugly, but it's exactly the same thing as associativity, which we just said. That's what associativity becomes. So it is better to use the usual way of writing. I'm not saying that we drop that. I'm just trying to look at it in a more functional way. So we will define such a thing which will share a lot of properties with the usual addition. Right? So how do we define it? So here is how we define it. So note that we are defining it. It's not given to us. That addition, at least I don't want to talk too much about in the sense that what is its definition, because it will take us into the foundations of mathematics. But here we can define it, and we are going to. So define as, if you take the equivalence class of A, modulo n, which as we said, this can also be written as a plus nz, and you take the equivalence class of B, which can also be written b plus nz, the output that you get is defined to be the equivalence class of A plus B, which can also be written A plus B plus nz. Okay, that is the definition. It's in some sense a very natural definition, but there is an issue here. The issue is, Suppose somebody takes the equivalence class of A. A is an integer. We take the equivalence class of A. And yeah, before I get there, so this is our definition and we write it like this. We use the same kind of convention that we use for ordinary addition. We will write it like this. We just rewrote the definition, right? So instead of writing plus of two things is equal to A plus B, the equivalence class of A plus B, we write it like this. This is much nicer to look at. So yeah, I hope that is fine. But what is the issue here? The issue is, suppose somebody picks an integer A and take its equivalence class. But it is possible, in fact it is very much possible, that it is equal to the equivalence class of some other thing. Right? A shares its equivalence class with infinitely many integers. Any integer in its equivalence class, call it A prime, will make this equality happen. All I'm saying is, if you pick A prime here, you'll get this equality. So A and A prime could be different, but they could have the same equivalence class. Similarly, B and B prime could be different, but they could have the same equivalence class. That's very much possible. So person 1, let's call her Alice. So Alice might follow this definition that we just gave and answer this equivalence class. And Bob might use A prime and B prime. So he's adding the same things, but the representatives that he's using to add are different. So he will obtain this as the output. Now, if this addition that we defined, even though we use the same symbol as for the ordinary addition, even though this, the addition that we defined, if at all this is a meaningful function, it shouldn't produce different outputs on the same inputs, right? Alice is given what input? This pair of inputs. Bob is given this pair of inputs, but they are the same inputs because this is equal to that and this is equal to that. Alice is getting this as the answer. She just followed the definition. Bob is getting this as the answer. He also followed this definition. If the two people get different answers, this is not a legitimate, or this is then just garbage, right? So can we check that Alice and Bob do actually get the same answer? Yes, we can. Because when can we say that these two equivalence classes are the same? If you followed the previous slide and did all the exercises and everything, these two things are same exactly when the difference of these two numbers is divisible by n. So just need to check. So this is a very important point, that there is a check here. Need to check that A plus B, or the equivalence class of A plus B, is equal to equivalence class of A prime plus B prime if the equivalence class of A equals the equivalence class of A prime and the equivalence class of B is equal to the equivalence class of B prime. We need to check this. But is it difficult? It is not at all difficult. So from the first condition, meaning from this equation or rewriting this equation, we can say A is congruent to A prime mod n. That's exactly what that equation is, if you followed the previous slide. And the second one exactly says that B is congruent to B prime modulo n. But now by modular arithmetic, A plus B is congruent to A prime plus B prime modulo n. Right? Just use modular arithmetic. But now this is equivalent to saying then the equivalence class of a plus b is equal to the equivalence class of a prime plus b prime. So the upshot is, the modular arithmetic of addition is what helps us, is what lies as at the heart of this addition. If modular arithmetic did not hold, this addition couldn't have been defined this way. And in fact, this is equivalent to the modular arithmetic of addition. You can do a similar business with multiplication, and I will write things down. But I hope this point is clear now. That using the modular arithmetic of addition, we have just repackaged it in terms of a new addition on a grisly object. I say grisly, but actually it's a very beautiful object. It's a folded copy of the integers. So the addition, or you could say, well, the set of integers, they kind of fold into this class of remainders modulo n, this set of remainders modulo n, so to say, right? You take all the integers, you forget things, and you only are sensitive to the information modulo n now. So you get this object. But fortuitously, the arithmetic of z also folds to preserve enough properties so that there is a legitimate dissension of the addition upstairs to this. We will write this down in a very neat fashion in a few slides, but I hope these words are at least making some sense. Okay, stay on this. Maybe if it is unclear, pick a particular value of n and work out some examples for yourself. Pick a value of n, maybe say 7 or 15 or something, and work this out, right? Yeah. Now you can do the same business with multiplication. So this time I'll be a little brief. So we have a multiplication on the set of integers, which consumes a pair and outputs what we call the product. And this multiplication function will be denoted like this. So just a change of notation. Cross of a comma b is what we usually write as a b or a times b or a dot b, just notational differences. And this enjoys a lot of properties. Like commutativity, etc. We will define a multiplication on z mod nz. So how do we define it? So we define, unfortunately, this cross and this cross, they look the same, but they are very different. This cross is the cross product of two sets. This cross is denoting multiplication, so let me change it. Let me not write a cross, let me write a dot. That's better. Less confusion. So we will define a multiplication here, which we again denote by dot. Right? We don't decorate this with a subscript or anything. It's already a very degenerate symbol to begin with. So we will define this function as, you can guess, the equivalence class of A, comma the equivalence class of B, or the product of these two equivalence classes is just the equivalence class of the product of representatives. So here we multiply them like usual. A and B are integers. We multiply them like usual. We take the equivalence class. And here again, the same Alice-Bob issue will arise. Alice may take these representatives. Bob may take different representatives. He will seemingly get a different answer, but he won't. He will get the same answer. And that is just the modular arithmetic of multiplication. So the well-definedness part here you have to check. Okay. And now having said that, let's talk about the properties that these two things enjoy. So properties of these new addition and multiplication. Most of it will be exercises. So first I will write down properties for addition. So the first thing would be, so fix some n. So let n is some natural number, and now the first property, 0 plus a, the equivalence classes, they sum up to just the equivalence class of a, trivial. So the equivalence class of 0 just behaves like the 0 of the integers. If you take an integer a and you add 0 to it, you get back a, and it doesn't matter in which order you add. So the equivalence class of 0 just behaves like 0 in this new world, in this new folded world. You can easily verify. Okay, and commutativity. Okay, just verify that doesn't matter in which order you add. And we have associativity. Right? We have that. I don't know if there are other properties. So I'll just name them. So this is called additive identity, which is to say that the equivalence class of 0 is the additive identity of the folded world Z mod n Z. That's what I mean by this qualification. This is commutativity, and this is associativity. Okay. Similarly, we have the properties for multiplication. For multiplication, we have, so first, what is the product of 0 with anything? It's just 0, easily checked. What about 1? Very easy to check. So 0 and 1, they continue to behave like they behave for integers. The equivalence class of 0 has the same behavior as 0 has for integers, and the equivalence class of 1 has the same behavior as 1 has for integers. Commutativity. So many times we just don't write the dot also. When we write product, we don't write the dot. And we have associativity again. All those natural properties that we saw for integers when we were growing up continue to hold in this folded world. Okay. So this is, I don't know what to name it, so I'll put a blank. This is multiplicative identity. This is commutativity. This is associativity. There's a little more I want to say. So this one is very nice. Distributivity. So I'll put a star here. Star says, so this is about the interaction between the addition and the multiplication. This is called distributivity. So let me verify distributivity. What is it that we are trying to see? What is the left-hand side? The left-hand side is this product, because by definition of the sum, the thing in the bracket is this, which is equal to, by definition of product, this equivalence class. Okay, what is the RHS? This is equal to, by definition of product, that thing which is by definition of addition. And now by the usual distributivity of integers, this is equal to that. So the distributivity of usual integers descends down to give you distributivity in the folded world. Very nice. As nice as things can get. And maybe I will make one point here. Subtraction. So another star. Subtraction. So for that, or maybe I'll say additive inverse. Let me call it additive inverse. Deserves a star. So note that this plus this is 0, or the equivalence class of it. This is for all integers a, right? And it is for this reason that we will denote, so this is just a point of notation, that this can be denoted like this, right? So for each element in the folded world, there is another element which if you add to it, you get 0. So this is called the additive inverse of that. It is unique. You can easily show that there is only one such equivalence class. And this is an explicit description of it. Right? So this property is called existence of additive inverse. And what about multiplicative inverse? You can ask a similar question here. You can ask, if given an A, there is a B such that this happens. This is 1. You can ask this question. But this is exactly the question of inverses that we raised in the previous lecture. This is same as saying AB is congruent to 1 mod n. So multiplicative inverses may not exist, as we saw. Additive inverses always exist. Multiplicative inverses may or may not exist, depending on the choice of a and n. It may exist, it may not exist. Okay, so I hope this was not overwhelming, and we are not done yet. We will still repackage things a little bit. So here is a very simple definition, which is as follows. Fix a natural number. Then we have this natural projection map from the integers to the folded world, z mod n z, which is defined in a particularly underwhelming way. Pi n of x is just the equivalence class of x. So it's not, it may feel like I'm running around in circles, writing the same thing in so many different ways. It's okay. It's okay. Just get comfortable with these notions and notations. The point here is not only about this course. All of this is so general, is so ubiquitous in mathematics, that if you digest it now, you will reap benefits later. And let me show you one particular way of looking at modular arithmetic, which I really like, using the natural projection. So we have this addition on integers, which I denote like this. So this is the usual addition on integers. What I can do is I can, of course, fold this out here and map onto z mod n z. So z mod n z I will write this way. Right? I may take two integers, add them, and then get the corresponding equivalence class modulo n. Or I could fold it here itself. So here I may fold out both the entries to map into the Cartesian product of the folded world. So what is this vertical map? What is this map? It just takes a comma b to the equivalence class of a comma the equivalence class of b. That's what that map is. Or maybe I'll write it like pi n a, pi n b. Right? I'm just unpacking the meaning of Cartesian product of two maps. So that's what this vertical map is, and of course we know what this vertical map is. The point is this. This is a very, very important point. That if you draw this horizontal arrow and call it the addition that we defined for the folded world, and upstairs you have the addition that you had for integers, then this diagram commutes. There is this word that we use, commutes. What does that mean? It means you start with something here, a comma b. You travel via this arrow, you get a plus b. You travel via this arrow, you get the equivalence class of a plus b. Okay, that's one way to reach here. There is another way to reach here, which is by following these two arrows. Start with a comma b. You apply this arrow, you become this thing. And then you apply this arrow, you become by definition or just by kind of change of notation, you become that thing. So when we chose this path and we started with a comma b here, when we chose the lower path, we ended up at this sum. And when we chose this path, we ended up with this thing. And those two things are equal. That's how this addition was defined. So the commutativity just means it doesn't matter which path you take. Right? It doesn't matter which path you take. That's what commutativity is. So modular arithmetic of addition is captured in this diagrammatic way. We have this kind of the full unfolded world of integers that descends down to the folded world in a very nice fashion. Everything just descends down very nicely. Similarly, we have the same story for multiplication. We have the usual multiplication of integers. You may fold out at either end. And this diagram also commutes. The commutativity symbol is denoted like this, or some people also write a hash. So that's how you denote that a diagram commutes. Usually when you draw a diagram, you mean that it commutes. There is no point drawing a non-commutative diagram. Right, so the same story goes for multiplication. So this is one very nice way to capture everything that we said in the previous discussion, that this diagram commutes. But of course, you need to know the definitions, but you could kind of say that the definition is getting motivated by this diagram. If I had asked, what would this arrow be so that this commutes, you would inevitably get what we defined it to be. So that's one way to just motivate the addition that we had here from a very formal viewpoint. Okay, so I think this is all that I wanted to say, but let me just add one comment that stay on these things. Don't rush this. This may feel overwhelming because so much notation has been introduced, but in no time you will see the simplicity of these ideas. Nothing is very complicated here. Everything is so civilized. Things will get a little complicated at some point, but as of now things are getting very civilized. But yeah, I want to add one more slide. I think I made it. So let me, just to illustrate something that we have gained from this exercise is the following. In the previous slide, we were drawing trajectories. Advancing by a. So if you start at 0, you can advance by, so a is 6 and n is 15. So we were advancing by a, then we advanced by a, and then we advanced by a again, but then 12 plus 6 was 18. 18 was nowhere in the set of remainders modulo 15. So then we said, well, replace it by the remainder modulo 15, and that was 3. And then you again advance, and then you again advance, but 9 plus 6 is 15. 15 is same as 0 modulo 15, so you came back. This is how we said it. But there is a much better way to say, or much more natural in some sense way to say it. Don't think of them as remainders modulo 15. Think of them as remainder classes modulo 15, the congruence classes modulo 15. I don't want to put brackets around everyone, so just assume that there are brackets around each of them. So each of these symbols, they denote congruence classes modulo 15. And advancing by a just means adding the equivalence class. So then you don't have to say that, well, you go out of bound and then you take remainder or anything, right? Because let's say you start at 0, you add the equivalence class of 6 to 0, you get the equivalence class of 6. You further add the equivalence class of 6, you get the equivalence class of 12. You further add the equivalence class of 6, you get the equivalence class of 18. But the equivalence class of 18 is the equivalence class of 3. So you don't have to say that, well, you replace something. You don't have to say something which has a semblance of artificiality to it. Right? So you're doing the algebra in under equivalence classes rather than usual numbers. And that just takes out the seeming or nagging artificialness. Right? And further you advance by 6, meaning you add the equivalence class of 6. You come to 9. And then you come back to 0. Okay, so this is how we can review everything that we did in the previous lecture. Just work with Z mod nz rather than set of remainders. Work with remainder classes rather than remainders. And that will facilitate a lot of exposition also for me in the next lecture, this way of doing things. It was a very long lecture. I'm not saying anything very deep, but it's just that the language may throw you off. But I assure you, it is worth it, it is useful, and it is not at all hard. Alright, so enough said. With that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.